Welcome to my lecture number 8 on Fourier series and Fourier transform. In this video, we are going to prove the following two equalities, the sum of the series using Fourier series and Parseval's identity. First one is the summation of 1 upon 4 n square minus 1, and that value is half. And second one is the summation of 1 upon square of 4 n square minus 1, and that is equals to 5 square minus 8 upon 16. Now let us start with a brief discussion on Fourier series and Parseval relation. In our previous lectures, we have discussed the Fourier series and Parseval's relation in detail. Now consider xt as a periodic signal with time period t0. Thus, the angular frequency omega naught is 2 pi upon t0, and that is radian in per second. Now we can expand this periodic signal xt as a summation of sinusoidals. In particular, we can have one DC coefficient A0 and the AC coefficients AN and VN, and AN with this cos n omega naught t and Vn with sin n omega naught t, where n will start from 1 to infinity, all positive integers. Now Parseval's relation for this continuous periodic signal, we can have the average power of this xt signal, and that we can compute as 1 upon t0 and x square t dt. For one time period, if we integrate, this will give you the average power, and that is rated as, this is a0 square, and power of individual components. So power of an cos n omega naught t is an square by 2. So it is half times an square, and this is bn square by 2, so it is bn square. And for all harmonic components, n equals to 1 to infinity. So we are going to use this Parseval relation and Fourier series to prove that summation. Now let us take. Now the first problem we'll consider problem 1. This summation 1 upon 4 n square minus 1, n equals to 1 to infinity, and that value is half. Now we are going to prove this one. For this, we'll use the half full wave rectifier. So if we use full wave rectifier, you will see the time axis, this is 1/2, the next one, all full waves. all positives. Okay, and you see this is the origin 0 and this is time period t naught, and the actual sine wave is having negative part here, and that is now made positive in full wave rectifier. So this signal is x of t, and in our previous lectures we have computed the Fourier coefficient for this full wave rectifier. So this is your full wave rectifier. And this full wave rectifier will have this xt as one average value, and average value is this one, and it is pi upon 2. So this is pi upon 2. This is the, sorry, not pi upon 2, it is 2 upon 5. Sorry. Okay, and these SC components are, so you see in this case this is showing some half wave even symmetry property. So it is having half wave even symmetry. Okay, and second one is it's an even function. So due to this half wave even symmetry, it will have only even harmonics, and due to this even function, it will contain only cosine terms. So it will have only cosine terms and even harmonics, and coefficients are 4 upon pi, and the summation, it is even harmonics 2 omega naught t cosine 2 omega naught t upon 4 n square minus 1, n equal to 1 to infinity. Now here you will see at t equal to 0, we can get, you see, this point at t equal to 0, and its value is clearly 0. So left hand side it is 0, and right hand side it is 2 upon pi minus 4 upon pi, and this summation, you see, all cos components at 0, cos of 0 is always 1. So numerator will become 1 always for all even harmonics, and it is simply 4 n square minus 1, where n equal to 1 to infinity. So if you simplify it, so pi will become 0, multiply here, so it will become 0. So it will give you this 1 upon 4 n square minus 1, that summation is this 2 upon 4, and that is simply, it is half. Okay, so it's very simple proof. Now this summation we can prove it also without this Fourier series. So we can have some alternative proofs. So second proof, this summation, you see, summation 1 upon 4 n square minus 1 n equal to 1 to infinity, that we can rewrite as this summation, it has two factors, 2n minus 1 and 2n plus 1, right? So this is n equals to 1 to infinity, and this one we can rewrite that the summation of the simple. So if I multiply by 2 here and divide by 2, so it is 2 upon 2n minus 1 and 2n plus 1. Now this one we can, this 2 we can replace as 2n plus 1 minus 2n minus 1 upon 2n minus 1 and 2n plus 1. Here 2 and cancel out, and 1 and again plus 1, it will give you 2. Here n equals to again 1 to infinity. So actually we are using partial fraction. So this will give you half, and this summation 1 upon 2n minus 1 minus 1 upon 2n plus 1. Now you see, if you put this series, so this summation this one n equal to 1 to infinity. Now this half is there, fine. Now if I put n equal to 1, then first one is 1 and next one is 1/3, and again n equal to 2 if I consider, then this will be your 1/3 and it is minus 1 by 5, and next one again if I put n equal to 3, then it is 1 by 5 minus 1 by 7. It's like that, it will continue. So this term minus 1 upon 2n minus 1 or 2n plus 1, it will continue like that, and you will see these terms, they are cancelling out, this and this, this and this, all will cancel out, and this is left out, and you see this value will become 0 as n is going towards infinity. Okay, so this will die down. So then the total result will be simply this 1 into half is half. Okay, now next we'll consider next problem. The second problem, so this summation 1 upon 4n squared minus 1, and that's squared, right? N equals to 1 to infinity, and its value will be pi squared minus 8 upon 16. Now you see, this is not easy to prove using simple mathematics. Here we'll be using Parseval's relation. So again we'll consider that full wave rectifier. So you see this full wave rectifier, this side, so this is your 1, this is 0, and this is your T naught, remember, and this is your T naught by 2 that we have considered, and this is your full wave rectifier xt, and you know that xt, the expansion is given as its average value is 2 upon pi minus 4 upon pi This is your cos 2 omega naught t upon 4 n square minus 1, n equals to 1 to infinity. Now first of all, we will compute the average power. Now you see, you look at this one. If I consider a sine wave, pure sine wave, then this is only the negative part of this one. But to compute power, first we need to take square and then integrate. So if you take integrate square, then again it will become positive. So therefore, we can say that average power of full wave rectifier is same as the average power of sine wave. And that we know that its value is half, and that we can easily calculate. So this is 1 upon t naught, and integration for one time period t naught, and sine square omega naught t and dt. So if I multiply 2 here and divide by 2 here, and then this 1 upon 2 t naught, and this one we can replace as 1 minus cos of 2 omega naught t and dt. So you see here it is 1 upon 2 t naught, and it is only dt for t naught, minus 1 upon 2 t naught, and it is cos 2 omega naught t dt. So it's a double frequency. So within one time period, total area of a sine or cos wave, it is going to be 0. So this is always 0. Okay, so it is t naught, so it is half. Okay, so if I use Parseval's relation, so using Parseval's relation, this average power is half. This is equals to this first one, this is square, so 4 upon pi square, and plus, then it is half summation of an square plus bn square, and here only you are having a n. Okay, so summation of, so this is 4, it is given this square, so that I will take first 16 upon pi square, and then the summation, it is 1, it is 4n square minus 1, and that square, n equal to 1 to infinity. Right? So this 2 and 16, it is 8. So therefore, you see, this is 8 times this one, 1 upon 4n square minus 1, that square is same as, it is pi square by 2 minus 4, and that is equals to pi square minus 8 by 2. And thus, and this is n equals to 1 to infinity. And thus, you see this one, this summation 1 upon 4n square minus 1, that square, n equal to 1 to infinity. It is simply pi square minus 8 upon 16. Okay, so this is proved. In the next video, we'll discuss. We'll start with the Fourier transform. Please keep watching, and if you like, then subscribe my video. Okay, thank you.